This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So yesterday we covered Laplace transform. We summarized the main things that you need to know about it, and also I included at the end of the lecture some of the proofs that I strongly advise you to work through. So in today's lecture we will continue using Laplace transform in the analysis of linear models. So I'll talk about transfer function. I'll introduce the definition of the transfer function, and I will present the algebra of block diagrams. So we will see how we can simplify series connections, parallel connections, and feedback connections of transfer functions. So algebra of block diagrams and transfer functions are bread and butter in this subject. So it's the sort of most important set of tools. We will present some others as well, but it is definitely one of the foundations, mathematical foundations of the subject. And then we will, if we have time, we'll go through an example, a more realistic example of calculating responses of a DC motor using Laplace transforms. By the way, this week we will already have covered a lot of material, and you will be able to practice a lot. So there's a lot of stuff now that you can do on your own. And tomorrow we will present some tutorials on Laplace transforms. But if you go to Ogata's textbook or Franklin and Powell textbook, you would find a lot of exercises. These are foundations, so there's a step change in the style of lectures. The first week was just introduction. There wasn't much to do. It's just sort of motivating things. But with this week, you already have heaps to do. So I'm just sort of indicating that this is the time to sit down and really apply yourself to the subject if you haven't already done so. All right, so we'll first motivate things a bit and then introduce the transfer function definition, and then go through the algebra of block diagrams, and DC motor. We will consider impulse and step responses. I will go quickly over calculations. They are all given to you, so you can work through them on the slides. But in the interest of time, I will just explain the ideas, and the steps, at a high level. But details we will leave for you to practice on, and we will spend some time through tutorials, looking at details of how to compute things. And then I will wrap up with conclusions. So transfer functions are fundamental in this subject. We will use them as a tool. We will use them for analysis and design of linear systems. We will, in today's lecture, link it to the impulse response. We already talked about impulse response when we introduced convolution representation of linear models. And then we will, introduce algebra block diagrams. You will see it's an essential tool. Often in an example, the first thing to do is to simplify your block diagram, obtain the transfer function of interest, and then analyze and design things. And then we will present also an example, more realistic example of a DC motor, so you can see actually what you can do with these tools. All right? So what is a transfer function? Look, if you start from first principles, you would often obtain a differential equation that looks like this. So that differential equation relates inputs and outputs. So we defined inputs and outputs before. We presented a number of examples where we defined these inputs and outputs. And we will just start from an abstract equation like this, right? So this can be, mass spring system, or it can be room temperature control, or car or cruise control in a car, or any other system we can think of. And what we want to do now, we want to translate these differential equations via Laplace transform into complex domain. We want to see what is an object that would capture this differential equation in Laplace domain. So if we assume zero initial conditions, right, in Laplace transforms, then we get something like this. So this is the Laplace transform of y, this is the Laplace transform of u, and then you get these two polynomials multiplying y and u. Does anyone see where these polynomials come from? Which rule in Laplace transforms are we using here? Sorry? Derivative. So, sorry? Linearity. Okay, linearity is one definitely. We also use the formula for derivatives with zero initial conditions, because Laplace transform of a derivative is s times the Laplace transform of the function. And higher derivatives, you have just s squared, s to the power 3, etc. That's where these polynomials come from. Note that the coefficients here, ak and bk, are exactly the same as coefficients in the differential equation. So when you assume zero initial conditions, you get exactly this expression. So note now that what we have here is, this red and blue, these polynomials, they depend on the model. They depend on the model. They depend on the differential equation. They do not depend on the inputs and outputs. It's just basically AK and BK coefficients come from the model. Y is the Laplace transform of, so Y of S is Laplace transform of Y of t, and U of S is Laplace transform of U of t, right? So, but these red and blue brackets come from the model itself, from the system, right? So if we divide everything by this red polynomial, we can rewrite everything by saying, well, Y, the Laplace transform of Y, is equal to this G times U, where G of S is B of S over A of S. I denoted B of S to be this polynomial, and A of S to be this polynomial, red polynomial. I use colors to relate them. So then this G of S, which is the ratio of B and A of S, is called a transfer function. What's interesting about transfer function? First, its simplicity, because if you think about G as some sort of gain, then input is sort of multiplied by this gain and you get the output. Obviously, everything is complex domain, right? But if you remember, voltage, in Ohm's law, voltage is, some proportional dependence with current. It's a similar thing. So this representation here, Y of S equal G of S, U of S, is very simple, right? Now, transfer function is basically capturing everything you need to know about the model of the system. So transfer function is really, you can say, the model of the system. All right. So that's the definition. That's the definition. Now, we would use this representation and this definition of transfer function for a range of different analysis and design tools. So how do we represent using block diagrams? Well, we would put this G of S transfer function inside the block. So all the boxes represent subsystems in your block diagram, and all the arrows represent Laplace transforms of different signals. So basically you have input arrow, that's U of S, right? That's multiplied by G of S, which is basically coming from your system, and that's how you get Y of S. So this is a simple sort of block diagram representation of a system using a transfer function. What's really useful to do here is to relate transfer function to impulse response. If you revise Laplace transform tables I presented yesterday, we saw that if U of S is 1, that corresponds to the impulse function, right? So Dirac impulse has its Laplace transform to be equal to 1. So if I apply impulse, its Laplace transform is 1. And then when I multiply, G by 1, I get just that Y of S is equal to G of S. So what does this mean? It means that the Laplace transform can be interpreted as, the transfer function can be interpreted as the Laplace transform of the impulse response of the system. Can everyone see that? So transfer function is really Laplace transform of the impulse response. You apply impulse to the input, you observe the output, take its Laplace transform, that's the transfer function of your system. How else can we see that, this is the Laplace transform of the impulse response? If you remember, the convolution representation of the system, then output is convolution of the impulse response with input. But when we take Laplace transform of all that, Laplace transform of the convolution is the product of Laplace transforms. So that's also how we can see. If you take inverse Laplace transform of this, you get exactly the convolution representation in time domain. So that's another way to see this. Okay? And that's exactly what I saw. Look, these steps I don't want to go through. They are really, every step is given there for you to sort of follow the derivation. But what's important is if I take Laplace transform of the convolution, this G star U means exactly convolution of the impulse response with U. That's exactly what it means. And then what is proven here is that so Laplace transform of that is really product of the Laplace transform of the impulse response and U. So basically what this says is if I look at convolution representation, take Laplace transform of that, I get exactly the transfer function representation in the complex domain. Okay? Are there any questions here? I'm changing gears, guys, so we will be going faster through material now. All right? But slow me down, ask questions if you are not following. All right. So I'll keep going because we have lots to cover. So know that a transfer function is, by definition, obtained with zero initial conditions. But sometimes in questions you might be asked to compute response for non-zero initial conditions. Bear that in mind. Bear that in mind. Okay? As we said, transfer function is Laplace transform of system's impulse response. And look, convolution is really difficult to use. When you look, so convolution is the integral of this sort of product of two functions. It looks messy. But when we go to Laplace domain, which have just a product of two things, it's very easy to deal with. And then we will often represent all subsystems in a system with the transfer functions, and we will show interconnections. Maybe output to one system is input to another system. That leads naturally to this notion of block diagrams, and in particular algebra of block diagrams. Sometimes we have a complicated block diagram of the system, and we might be able to simplify it as a simple transfer function with simple one input and one output. So we will look at that in a moment. So this is what algebra of block diagrams means. So what we have here is think of what is on the left-hand side are more complicated block diagrams with many subsystems, right? And what we want to represent it as a simple transfer function with one input and one output. Know that all of these on the left-hand side have single input u, and they have a single output y. So, but this is messy, all right? So when I look at this, I'm not sure what's the transfer function that relates u and y, right? So algebra of block diagrams basically simplifies this complicated picture into a single transfer function that relates directly u and y. So what's a claim is that the relationship between u and y, let's say in this case, is actually given by this sort of single transfer function. Now the question is, how can we prove maybe something that looks like this, complicated on the left-hand side, into something simple that is given on the right-hand side? That's called algebra of block diagrams. And by the way, if you understand and maybe even memorize formulas for these basic cases, you would be able to simplify much more general block diagrams by subsequently using each of these cases as steps in simplification of your block diagram. So these are like basic operations that you need to memorize and learn, right? So because they are so important, we will prove them. So we want to prove that each of these basically representations are correct. So let's first look at the series connection. By the way, the first row is a series connection of two subsystems. The second row is a parallel connection of two subsystems. Then we have the last two rows correspond to two different feedback systems, right? What's important in feedback is the following. Note that this plus before u in both cases means that the signal here, this error signal, is really u that comes with plus, and then y that comes with minus. So this signal here, input to C of S, is really u minus y. Okay? So that's what this summary means. But because of this minus, you would find that in the simplified block diagram, you have here plus. So if you had here plus, then this would change to minus. Why I just present minus is, well, in feedback systems, we typically use negative feedback, but the formula can be easily changed if you had here different sign, right? That's very important to pay attention to. You always have to check the signs at the inputs of your summer, right? Comparator, and then this sign in the feedback, right, would be basically opposite of this sign that you get in the simplified transfer function. Okay. Pay attention to that. There is a big conceptual error by using positive feedback instead of negative feedback. All right? Because typically positive feedback would cause problems. Negative feedback has stabilizing, nice effects. Positive feedback often would have, adverse effects on your system's behavior. So that's why conceptually, students may say, oh, it's just a plus or minus, and you are penalizing me for this. But there's a difference between wanting to save the world or destroy the world, right? That's the difference we're talking about. So plus or minus may mean that, okay? Okay. So let's look at the first row. What we want to show is that the series connection, transfer functions of the series, transfer function of the series connection is really the product of the transfer functions of the individual subsystems. How do we do that? Well, we always need to look at definition of the transfer function. Definition of the transfer function is y of s divided by u of s. That's the definition. How do I see this? Well, if I go here, for instance, well, what is g of s? Well, g of s is y of s divided by u of s. Yeah? So I start by wanting to find what is y of s divided by u of s, because that's the transfer function. So let's look at the series connection. Well, what is the transfer function of the first guy? By the way, I introduced this intermediate variable z, which is the output of the first subsystem, but that's the input of the second subsystem. The same variable, z. And then, what is the transfer function of the first subsystem, well, it's the output of that transfer function, which is z, divided by input of that transfer function. How about the transfer function of the second guy? Well, that's, y, the output of the overall system, divided by z. Know that z can cancel here, and what we end up with is exactly your sort of definition of a new transfer function for the combined system. So we just proved what I just said, right? Because f is really z over u, and g is y over z. So basically, the transfer function of the series connection is the product of the transfer functions of the two subsystems. Very simple algebra, right? But very, very useful. Very useful. Okay. Let's look at the parallel connection. Now, I again here introduce two variables, z1 and z2, and then I'm asking myself, what is y of s divided by u of s? Because that's the transfer function of the full system. Well, what is y of s? Well, y of s is the sum of z1 and z2, right? And then if I just sort of look at, I split them, right? So z1 over z2 over u is really z1 over u plus z2 over u, right? Well, but what's the definition? Well, this is exactly the definition of f, and this is the definition of g. So we've just found that the transfer function of the overall system is really the sum of the transfer functions of two subsystems. All right. Let's go to the next one. This is a bit trickier. It just requires a bit more algebra, but it's quite straightforward when you think about it. So again, we want to find what is y of s over u of s. So we need to now introduce this e of s. E of s is an auxiliary variable that would help us simplify this block diagram. So what is e of s? Well, it's by definition u of s minus y of s. But what is y of s? Well, y of s is really like a series connection from C, so that we have series connection from input E to output Y. You see, what we've just done in one of the previous slides, we said if we have that E is the input to this series connection, well, the transfer function of that series connection is the product of the two transfer functions, right? So since I define this signal E, I can write that Y is equal CGE. I'm using here series connection. What is E? Well, E is U minus Y, but Y, I just found it to be this, right? So I can substitute it, right? Why do I have here minus? Because of the minus in the diagram. If the minus was plus, I would have to use here plus, so things will change. So what I do now, note, I have here E, and I have here E. What I can do, I can take this minus CGE on the other side, and then I would have 1 plus CG multiplying. I divide by that, and I get that E is exactly equal to this. Right? And then, in the end, I just use this E in the first equation. I calculated E as a function of U, so I substitute this E back here, and I get that Y of S over U of S is equal to this. Now you can see why, if there was a plus here, that plus would turn into plus here. That plus here would turn into minus here, because when I take to the other side, it becomes the minus. That's it, right? We've done it. So, look, people ask me sometimes, do I need to memorize that? Well, yes. So, yes. It's easy for me. Yes, yes, you do. No, actually, I wouldn't stop there. You need to be proficient in using this in problems. It's not just memorizing. You have to really understand it. You have to be proficiently using this in any problem I give you. So yes, I mean, it's not just passive knowledge, it's active knowledge. Okay? Here is the last one. We will skip over that. I mean, note that now we have that there is some block in the feedback. In the previous case, we didn't have any block in the feedback. Now we have some block in the feedback. Now, look, rather than going through calculations, which are pretty much the same as in the previous slide, right? Let me just outline a difference between these two and how you can memorize the formula more easily. So what I would call So how you can think about the formula that is general, right? That applies to any feedback system. So look what is in this top equation. Well, in the top equation, you have basically the open loop, like a transfer function that relates E to Y. I would call it, well, it's not just open loop, it's just the transfer function that relates E to Y. It's a transfer function in the feed-forward part. And what is the transfer function in the overall loop? If I go from E all the way to this, signal here, it's still the same in this case. So on top, you need to write CG, whatever is in the feed-forward part. What you write here is basically transfer function of the whole loop, right? In this case, these two things turn out to be the same because there was nothing in the feedback loop. In this case, however, there is a difference. So what is on top here is just G. That's the feed-forward transfer function. And what is at the bottom is so 1 plus the loop, a transfer function of the full loop. That's easy to remember then. Okay. And then only this plus or minus would depend on the plus or minus of the comparator. Okay. Now, I might give you a block diagram with 5 transfer functions with parallel connections, series connections, feedback connections. You would have to be able to use this sort of simplification step by step to simplify any given transfer function into a single, like very simple block diagrams with the input, output, and transfer function that's now complicated and depends on all the transfer functions of subsystems. This is often useful when you're dealing with true systems because one transfer function may be your plant, another transfer function might correspond to an actuator, another transfer function might correspond to a sensor. So you have to be able to connect all these things into a simple transfer function, which is often the starting point in the design and analysis. Here is one example. So I also present this because we will come across block diagrams like this more in the subject when we talk about sensitivity transfer functions. What's so special about this block diagram? Can someone tell me? This looks pretty much the same as feedback connection, but there's an important difference. We have 2 inputs. Now, where you have 2 inputs, you have to do things slightly differently, right? So how do we find transfer functions in this case? Well, actually, in this case, you do not talk about a single transfer function. You talk about multiple transfer functions. One transfer function relates this input R to the output Y, and another transfer function links DO to Y, right? So later on, we would give a special name to such transfer functions. They're called sensitivity transfer functions, and they are very useful for analysis and design. We will talk about them later. But what you can definitely say that Y is equal to some transfer function times R plus another transfer function times DO. Now, how do I get this TO and SO? Well, I get them by setting the other input to 0 and then applying the algebra of block diagrams directly to that new system. And then the other transfer function is obtained by setting the other input to 0 and then applying again algebra of block diagrams. So how I got this T0 and S0, by the way, this is called sensitivity transfer function, this is complementary sensitivity. They are so important that we will give them names later on. But this is where we are using algebra of block diagrams. Now, I would perhaps encourage you that you verify indeed that T0 and S0 can be obtained when we set either R equal to 0 or D equal to 0. And then just find transfer function from a single input that remains and that output. By the way, this thing here, again, is a consequence of superposition principle. Because we have 2 inputs, right? So the output, the total output, is really the sum of contributions of each of the inputs. That's sort of superposition principle in disguise, right? All right. So, all right, before we go on to this example, I just want to check if there are any questions. Yep.
I'm assuming that this logic translates linearly from 3, 4, 5.
Yes, yes, definitely. Moreover, you will see later that we might decide that this guy is not an input. We may decide to say, well, we are actually interested not in this as an input, but maybe this E or U might be, output. So this Y may not be defined as output. We might say, well, actually, the output I'm interested in is U, right? And we will obtain 8 different sensitivity functions, either when, so there will be 4 inputs in general, right? And we might decide either Y is the output of the system or U is the output of the system. Note that the definition of the output of the system is it's the variable you're interested in. That's the definition. So if you are interested in actuating signals, right, then, that would be the output by definition. Right? When would you be interested in output signals? Well, you might want to say, well, would the actuating signal be very large? Right? When I solve my problem, I design a controller, well, would my controller require or produce very large control signals? Why is this significant? Well, first, large input signals might saturate your actuators. They also may mean that you are applying a lot of energy to control your system, a lot of effort. Like large control signals mean a lot of effort. So that's why we might be interested sometimes in U being the output of the system. Later on, we will consider a much more general version of this block diagram, where instead of 2 inputs, we will have 4 inputs. We will introduce also disturbance at the input here, and we will add also another signal here, which would be the noise. Right? And we would be interested in all possible transfer functions from each input to each output. Why are we interested in all these transfer functions? Because transfer functions tell us the relationship, how a certain input affects certain output, right? So if the input is a disturbance, then we would say, well, this disturbance affects the output in this way, if we understand the transfer function and its properties. Yeah? Any other questions? All right. Let's now look at a DC motor example as just a bit more realistic situation. It's not just mathematics, it's related to a physical system. So what we are asked to do is to determine the impulse response of the motor for the input being supply voltage and the output being the angle of the shaft. So here I'm saying, so you have in a DC motor, you have a rotating shaft. So you apply certain voltage and the shaft would rotate. So the angle, in this case, is the output. So that's the first first part of the question. The second one is determine step response. In the first case, we were looking at impulse response. So I'm applying impulse to the input, and I'm observing what would change to the shaft as the output, right? Here I'm saying, let's apply step response, so step input, step voltage, but I'm interested that in output, which is the angular velocity. So I changed from angle to angular velocity. I'm saying I'm no longer interested in angle, I'm interested in angular velocity. So we want to find either impulse response with angle as the output, or step response as angular velocity as the output. And we would use both block diagrams and Laplace transforms. So pretty much in this example you have everything, because you would need to do partial fractional expansion of an expression in order to find the solution. Let's see what we are dealing with here. So what you have here is, a motor. So the coils in the motor are approximated by a series resistance and inductance. It's an approximation. And by the way, this back electromotive force is sort of because there is, so this sort of flow of current would cause movement. Well, there is an extra drop in voltage due to, because it causes movement, right? So that's due to, that causes this back electromotive force. So we assume that sort of drop in voltage is proportional to the angular velocity. Theta is the angle of the shaft, and theta dot is the angular velocity. We also we assume that there is some inertial load attached to this shaft. So this shaft would have to move some inertia, mass, right? And then also there is some damping friction. So we assume that there is also torque due to friction, and it's proportional again to the angular velocity, theta dot. So these are all assumptions. So if you look at all the linearized equations, so linear motor equation is the torque is proportional to the current in the through the coils, right? Newton's second law of motion is, well, the inertia times the angular acceleration is equal to the sum of all torques. Well, in this case, there is this torque caused by the current, right? That's basically moving the whole thing. And then there's this minus the friction. That's this guy here, right? And then, using Kirchhoff's voltage law and the simplified circuit diagram there, we have that the driving voltage U is the input to the whole system, right, is, equal to this. So this is basically just, simple electrical circuit theory. So what we presented here are equations that you get from first principles and assuming linearized model for the motor. Often this characteristic is non-linear, but we assume it's linear, so it's already linearized for us. It's an assumption. So note that these three equations now represent the model of the system. Three equations, because there are three different physical laws that we use to sort of describe the behavior of the system. What is the output? Well, in our examples, output can be either angle of the shaft, theta, or it can be angular velocity. So we will, depending on the question, we would either assume that output is theta or output is theta dot. But the input was always U, the voltage, the driving voltage. Yeah? So you apply U, and then this shaft starts moving. How does it start moving? Well, it will depend on these differential equations. It will depend on the motor, and the motor will basically determine what sort of R, L, and this K1 you use, because these things depend on your motor, right? So these equations depend on a particular motor. A larger motor would have different constants from a smaller motor. The differential equations will be different. So how do we approach this problem? Well, we want to use Laplace transform, everything we've learned. So let's take Laplace transform of all of these time domain equations. So this is a time domain equation, this is a differential equation, this is a differential equation. Let's take Laplace transform all of them. Well, that's what we get. What is given in red is what we obtain by applying Laplace transform to these equations. By the way, I kept here, dependence also on initial conditions. You have here theta 0 or theta dot 0. They are coming from the initial conditions. I'm using Laplace transform for the derivative, right, to write these guys. So this should be now as no surprise. So going from black equations to red equations, we've done it in the previous lecture, and also in today's lecture we talked about it. All right, so now you may say, all right, well, this is all good, but what's the relationship between U, the input, and some output? What is the relationship? Well, it's not easy to see because we have three equations. We have three equations. We have to have a single equation that relates input and output, right? So that will require a bit of work. So if we assume zero initial conditions, then we can, I just summarized it for you in this table. Well, every of the sort of first principles laws can be translated into an equation in Laplace domain. But actually, if you think a bit more carefully, well, these things here, it's sort of like, it's almost like subsystems talking to each other, right? So I can represent, all of this in a diagram. This is not a block diagram yet. It's just a diagram that basically says, well, look, if I think about the torque, as input to the Newton equation, well, the output, this torque would cause the thing to move. So shaft angle would change. But then shaft angle, does affect the Kirchhoff's law through back electromotive force. We said that back electromotive force is proportional to the theta dot. That's how this shaft velocity goes back, and affects our Kirchhoff's law. Kirchhoff's law is also affected by the input U, like the voltage, right? And then what is the outcome? Well, as we change the voltage, that will change the current. But current affects the motor, and motor creates torque. So now this is one example where you see something that resembles a block diagram. This is not yet a block diagram because I didn't write down precisely comparator. I didn't really write each block using its transfer function. But you can easily go from here. So I would say, exercise, redraw this diagram so that you get a block diagram where each block is represented by its transfer function. You can do that. Obviously here in this block, you have two inputs, but you can really, first subtract them or add them and then feed them into a block with a single transfer function. So you can use comparator, right? So this is very easy, but now, all right, well, we need to simplify this somehow. We want to get a relationship between U and Y, right? Because we are asked to solve what is Y given certain U, right? Well, here is what direct calculations yield, and I won't go into details. I presented each step in the calculations. So I'm more presenting like a high-level view. We will look at tutorials how to do the detailed calculations as well. So what you get when you eliminate some of these variables, you get that a Laplace transform of theta divided by Laplace transform of U. U is the voltage, theta is the shaft angle, is equal to something that looks like this. Where all of these constants now, K1, K2, they come from the model that we presented earlier. Now this is very, very messy. Why? Well, I would like to apply certain U. So theta, for instance, angle shaft, Laplace transform of that, would be Laplace transform of U times this. So when Laplace transform of U is 1 over S, that's a step signal. When Laplace transform is 1, that's an impulse. So we were asked in the first instance to apply impulse. Basically, this is 1. And we were asked to observe how shaft angle changes, right? So that means that when U is 1, then theta is equal to all of this. Now, can I find this thing directly in Laplace transform tables? Probably not. Probably not. So what do we need to do? Partial fraction expansion. Now, partial fraction expansion, because this guy is messy, it's hard to apply directly this partial fraction expansion. So it's convenient to rewrite this thing here, the denominator, in this way. Know that everything is multiplied by S. Look, there is S here. I can take S outside, and there is also S here. So I can take this S outside, everything in here, right? And multiply with something else. But then what I multiplied S with will be like a second-order polynomial. It's very convenient to rewrite this second-order polynomial as something that looks like this. Why? Because these terms are nicer for partial fraction expansion. So if you assume, certain things like that this condition holds, by the way, R, J, B, L, and all of these constants come from the model. So they can be found in the model, right? If you have a condition like this, then it turns out that these T1 and T2 are real numbers. You can check that. But, I'm just sort of stating that that's the case. By the way, this example is done at a very high level of generality. Typically, I would give you specific constants, and then all of these calculations would be much simpler, right? Because you would have T1 is equal 1 or T2 is equal 2, and off you go. It's not as, but the example is given really at a high level of generality. We can deal with different DC motors in this way. So now we have a representation. If this, we assume this holds, then T1 and T2 are real, and this is my transfer function that I need to deal with. So now we need to apply partial fraction expansion. What's a partial fraction expansion? It's basically representing all of this as a sum of these three terms. Yeah? And now you can calculate each of them, by first assuming this form. By the way, you can calculate them also the formula I gave you. A1, A2, and A3, they are constants that they are residuals that I gave you formulas for. Right? So I gave you formulas for these guys. But here, there's a different method used. So you calculate A1 by multiplying all of this above by S, and you have to have that whatever is on the left-hand side is equal to the right-hand side. After some algebra, you get that A1 is K. So that's after some algebra. You can compute A2 and A3 in the same manner. What you get is basically this. You have that the transfer function from u to theta is given by that. After partial fraction expansion, it's equal to that. And then if we want to find what theta of t is for a particular theta, so u of t, we just need to substitute the Laplace transform of u and then find what inverse Laplace transform of theta is. Since u in the first example was u of s is 1, we were applying impulse, then theta is equal to this. What is the inverse Laplace transform of a1 over s? Well, it's just a step function times a1, unit step function times a1. And then inverse Laplace transforms of this guy and this guy are corresponding to these decaying exponentials. So this can be read off directly from transfer function tables. And what do we get? Well, we get this response this is basically impulse response of the system because we assumed u to be equal to 1. So here is what you can do in Simulink. You can simulate the whole thing. So what is given here? Red is the total impulse response. So we assumed here also that constants in those formulas are given by these numbers. This is just a specific situation, right? First, we derived everything for any DC motor, right? But now we are simulating these for a particular DC motor. What is given also here are so-called fast transient and slow transient. Know that these are exponentials. Blue and green are exponentials, and they correspond to these two exponential terms that we found in the impulse response. So know that one of the exponentials would decay faster or change faster than the other. Note that one exponential can be related to mechanical part of the system and another one to the electrical part. You have a very clear sort of physical interpretation of these things. Total response is given by the red curve. And A1 there is also the first term, so that's just this guy. So what we are plotting, yellow is A1, so yellow is A1, and then we have two exponential terms which are given by blue and green. Red is the sum of all of them. Red is basically just the sum of all of them. Okay? So what can we see now? If I apply impulse input, basically what does this mean? It's like I have a switch for the voltage. I just apply infinitely large voltage and I just turn it off. If you apply such a voltage, impulse input to the system, the shaft will sort of move and then converge and stop eventually. Like it converges to a certain value. It changes, the shaft angle changes from 0 to some value. Right? So that's what we just learned. This is very physical, right? If I apply impulse voltage, shaft will move and exponentially converge to a certain value. Right? here is another question that we were asked. We were asked also to consider angular velocity as the output, but then we apply step voltage as the input. If you consider angular velocity as the output, note that this was the transfer function of input voltage to angle. But what would be Laplace transform of angular velocity? It's s times theta. So if I take this s here, multiply theta, well, that's the Laplace transform of my angular velocity, right? That's my new output. So if I assume that my s times theta is my output, I take this s, take it here, and that's my output now. And my transfer function changed. How it changed? Well, now transfer function is just this term. There's no s anymore. But what this question says, well, that's the new output. But now u, I want to apply u, which is a unit step function. What's the Laplace transform of the unit step? 1 over s. So what you would find is that you get the exactly same thing as in the first part of the question. So if you define this new output as given there, but then you apply 1 over s as the input, you are dealing with exactly the same beast. And exactly the same calculations give you exactly the same response. So what this tells you? Well, you know, total speed response, which is the red curve, it's basically now how angular velocity changes when we apply step voltage. So we go from 0 voltage to, let's say, 1 volt, right? So what this says is that angular velocity will start speeding up, and it will convert to some constant speed. So that's what this diagram says. So you see, what we've just done, and I hope you appreciate it, it's not just maths. This is a really insightful analysis of a physical system using all the tools that I presented in the last couple of lectures. You will learn more and more of how to do this for any physical system, right? So it's a very cool set of tools that we will learn in this subject. All right. I just want to wrap up. So what we did in today's lecture, we talked about transfer function, we talked about algebra of block diagrams, and we also talked about how to apply this. We demonstrated how to apply this on a physical example of a DC motor. Note that the definition of the output is very important, right? We in the end got the same response, but the meaning of response was totally different in the two cases we considered, right? Are there any questions? All right, thank you very much. I'll see you tomorrow. Hello.
May I ask what's the meaning of this one? Why this one have to be bigger?
So,
Yes.
let me just turn this off. What you get inside the brackets is a quadratic function. So if you take s outside, you will have that s multiplies some quadratic function.
Yes.
So that quadratic function might in general have complex conjugate poles. In general.
Right, conjugate.
Yeah, it can have, it's a quadratic function. So
Okay.
s squared plus as plus, b. So that can have complex conjugate poles.
Okay.
This condition here guarantees that it doesn't. And since it doesn't, then there are two real poles. And then I can say that one pole is minus 1 over t1, and another real pole is minus 1 over t2. But this is basically that the square root, whatever is inside the square root, when we're calculating the poles of that quadratic polynomial, roots of that quadratic polynomial, that's basically giving you real roots of the polynomial. So I can rewrite that polynomial as a product of two terms that look like this, and that implies that there are two real roots rather than complex conjugate roots. So that's where it comes from. Take s outside, you get the quadratic polynomial nest. If you want that quadratic polynomial nest to have two real roots, this condition has to hold. If this condition holds, you can rewrite it in this way.
Okay.
Yeah?
So I just wanted to ask, in partial fraction expansion, the highest power in numerator will always, for the sums that we get in the example, the highest power of the numerator will always be less than the power of the denominator, right?
Right. Yes. So we would consider causal systems. We'll talk about this a bit later. I mean, in all physical models, the number of zeros is small.